This video is kind of funny because I started this section by saying, we've already done the fundamental theorem of calculus. You know, the definite integral of a rate of change is the total change. And then we said, well, let's write that a different way. And we did it, and we wrote this. So at the beginning of the section, we wrote this. The fundamental theorem of calculus says that we can evaluate a definite integral of a derivative as the difference between the original function, the antiderivative, and antiderivative. Any antiderivative will work. And in words, what that says is, again, the definite integral of a rate of change gives the total change of the function. This is nothing new. Actually, nothing new. This is the first video of this section. Not Jason, nothing new, but actually nothing new. But we have another way that we can view the fundamental theorem. It's not a very impressive magic trick. All we're doing is adding f of a to both sides. We do that. We have f of b by itself. And the other side is just f of a plus the definite integral. So nothing super crazy, but here's another way of viewing the fundamental theorem. Is that the value at the end of an interval is where do we start plus the total change. This may seem a little silly, but there's a few ways that this can pop up. Okay, maybe we're looking at a velocity function. We know where we started and we knew how far we've gone. We have to add those two together. That's exactly what we've got here. So let's look at an example. Suppose f has the derivative of little f. Again, if the derivative of big F equals little f, that means big F is an antiderivative. Remember, that's the definition of antiderivative. There's just an f right there. It's a little cut off. So big F is an antiderivative, little f is the derivative of the antiderivative, which is kind of weird to say. So again, this is a graph of a derivative, right? This is the derivative of big F graph. And suppose that we know that f of 0 equals 5. So big F started off at 5. Well, we can use this theorem to find what f of 1 is. Again, this value right here is just little f of 1. That's not what we're asked. We're asked, what is big F of 1? Well, according to the fundamental theorem of calculus, the value of f at 1 is just the value of where we started, plus the integral from 0 to 1 of the derivative. And again, our variables are t, so we're writing dt instead of dx. And f of 0, we know. We were told what f of 0 is. F of 0 is 5. And the integral, we can find that out. Remember, a definite integral can be found by looking at the area, or the signed area more specifically, the signed area under the graph. So it's the area from 0 to 1. That's a triangle. A triangle has area of 1/2. So f of 1 is 5.5. And you can do that for each of these. So get some practice, pause the video, and try to find out what f of 2 is, and f of 3 is, and f of 4. Let's see if we get the same answers. So similarly, f of 2 is going to be the starting value plus the integral up to 2. So now we're looking at this whole area up to 2, which is an area of positive 1. So this definite integral, this value is 6. Now for 3, we're going backwards. We have this positive red area, or sorry, this positive black area. But now we have this negative 1/2 area. Remember, integrals are signed area. Or you can think about this function as a rate of change. The rate of change is positive all around here. And the rate of change is negative down here. So we were going forwards over here. Now we're going backwards. We went forwards 1. We went backwards 1/2. So we're actually the same place that we were at f of 1. Again, 5.5. And again, likewise, at 4, now this green area is negative 1.5. Now we've gone further backwards than we went forwards. We started at 5. Then in the first 2 seconds, we went 1 forwards. And then in the 2 seconds after that, we went 1.5 backwards. So we're now half of whatever backwards from where we started, which looks like this, and we'll get an answer of 4.5. All right, and this is another way that we can use a fundamental theorem of calculus. Again, it's confusing because it looks like a function, and it is a function, but this function is the derivative of some other function. So it's always confusing. Are we talking about a function? Are we talking about its derivative? And then, things hold true that if the derivative is positive, the function is increasing. If the second derivative is positive, the function is concave up. Just question of what function are we talking about? There's so many functions. All right. We'll get some more practice with this in this last example, as well as the next video, which has just some homework problems. So again, capital F is the antiderivative of little f. And we're showing little f, the derivative of capital F. So this graph, again, is the rate of change, big F. And so what we're wanting to know is, where does big F have a maximum and minimum? Now, there's a couple ways of doing this. Remember in chapter 2, derivatives, we said a function has a max, well, let's not say max, has a critical point when its derivative equals 0. Well, where does the derivative equal 0? This is a graph of the derivative. This is where the derivative of capital F equals 0. Not to be confused with this point, this is where the derivative of little f equals 0. Not the same thing. That's confusing, I know. But we're looking for the maximum of big F. Let's find when the derivative of big F equals 0. This graph shows the derivative itself. And this is when the derivative equals 0. But is this actually a maximum? Well, here's a critical point for sure. Notice, again, this red graph is the derivative function. So the value of this derivative function's positive on the left. That means f is going up to the left. The value of the derivative function is negative over here. That means big F is going down over here. So this critical point, big F was going up and then big F's going down. We have a critical point. Yeah, this is a local maximum. All right. Local maximum of capital F, not a local maximum of little f. That'll be our answer here. Another way of doing this is saying that if we want to use a chapter 3 method, We could also say that f of t is, well, where did we start and how far have we gone? Now this is kind of weird. Oh, we shouldn't actually use t here. That's not something we mentioned too much. But if we're using t in our limits, we shouldn't use t as our variable. I wouldn't worry about that too much. It's not going to be a big thing for our class, I think. But it's just a little thing that these should never be the same. All right, so this is a chapter 3 way of looking at it. Remember, this over here is the area under f, specifically the signed area under f between 0 and t. So if t were 1, we'd be adding this area. But we can make it bigger, right? Let's also add this area. But we can make it bigger. Let's also add this area. We can't add any more area to make it bigger, right? Because as soon as we start adding more area, now this is negative signed area. So we don't want to add that part. So this is the most area that we can add. This is where f is going to be biggest, because this is where that definite integral is the biggest. When t is 3. When we're integrating, right? This is the biggest when t equals 3. Oh, also, I just realized our variable is t here. And our variable is t here. But yeah, that's another way of seeing it. Super weird. We got some more practice with this in the next video, but that's kind of what's going on. Using the fundamental theorem of calculus, we can also write our function f of t in this way. And this is the area under the curve, the signed area. We just have to look at this graph and say, well, we can maximize this by seeing when the signed area is the biggest. And this is when the signed area is the biggest, when t is 3. Because as soon as t is bigger than 3, we start adding negative signed area, which is going to make things smaller. All right. So again, 2 ways of getting the same answer, one with chapter 2, one with chapter 3. Let me know if you have any questions. It's a little weird. And we got some homework problems coming up right after this. Sounds like I'm taking an ad break. I can do a commercial for commercial for Wacom tablets, which is how I write your stuff. Anyway, bye-bye.